Hello, welcome back to Math 152. Because of class cancellations tomorrow, this is the pre-recorded lecture videos. It's going to be two videos, and this is the first part of the videos on complex numbers. So let's suppose that the only numbers that you know are the counting numbers, also known as the natural numbers, which is numbers such as 1, 2, 3, 4, 5, 6, so on and so forth. And if you look at these equations and you go through all these numbers that you know, you will find that x plus 1 equal to 3 has a solution, and the solution is x equal to 2. But if this is the only numbers that you know, and you look at this equation, x plus 1 equals to 1, and you go through all these numbers and try to find an x that will satisfy that equations, and you will find that none of these numbers will help you solve these equations, which means that if you only know natural numbers, this equations does not have the solutions. So now we know that the solution for this equation is actually x equal to 0. But the concept of 0, historically speaking, does not exist for a very long time. People doesn't find there is a need to define a numbers to give the concept of nothingness a number. So for a very long time, this equation actually does not have a solution. So suppose now we know there is a concept of 0, there's a number 0, so on and so forth, and we are now invent, so to speak, a slightly larger class of numbers. Let's say it's a set of integers, which consists of all the negative numbers. It also includes 0, and then it also have all the counting numbers. So now suppose we know better now. The numbers, the type of number that we know, are these numbers which we call integers. And you look at this equation, for example, you will find a solution. So this equation has a solution now, and the solution is x equal to -1. But if this is the only numbers that you know, and you look at this equation, 3x equal to 1, and you go through all this number here, you'll find that none of the numbers will give you 3 times of that numbers equals to 1. And again, restrict to this set of numbers, you'll say that this equations does not have a solution. Now you know that solution actually does exist, and the solution is x equal to 1 over 3. So in order to make sure that this equation has a solution, we will have to invent a slightly larger class of numbers, which are called rational numbers, right? So the set of rational numbers consists of all the numbers of this form, a over b, where a, b are integers, when b is not equal to 0. Even now, with the concept of rational numbers and even with irrational numbers and the concept of real numbers, if you look at this equation, x squared plus 1 equal to 0, and you go through all the x real value x, you will see that, again, this equation does not have a solution. So we will have to invent, again, a slightly larger class of numbers. And that class of numbers are known as complex numbers. And those are the numbers we are going to look at in these sections. All right. So in fact, we are going to define I as a number where the square of that numbers is equal to -1. So once we have this, we'll be able to talk about in general what is a complex, how is a complex numbers looks like. Now all these concepts are known actually long before Eulers and Gauss, but Euler and Gauss are the two mathematicians who popularized the use of complex numbers, especially the use of this numbers where this number I, where I squared is equals to -1. You can also write I as a positive square root of -1. So these are clearly not real numbers. In real number system, we do not have I where something's the I square, whereas I square is equals to -1. So we do not have that. Now I here probably stand for imaginary, and I is a number where the square of that number is equals to -1. Now in general, complex numbers can be written in the form of a plus ib, or you can also write a plus bi, where I squared is equals to -1. Now, when we write a complex number like this, the requirement is that the a here and the b here are actually real numbers, okay? So a and b are actually real numbers. So a complex number will be a number in the form of a real number plus b, which is also a real number, times I. And I is such a number is a number such that I squared is equals to -1. Now, some terminology. So a here is known as the real part of this complex number. So if you call this complex number z, then a is known as the real part of z, and this is a notation for it. RE stands for real, so real of z is a number, it's a real number, which is a. Now, the b here is known as the imaginary part of that complex number. So even though the terminology is that b is an imaginary part, b is still a real numbers. So the notation is IM stands for imaginary. So imaginary part of the complex number is this number b here, where b here is a real numbers. Even though the name is imaginary, be careful, imaginary part of a complex number is still a real numbers. So for example, we can have z equals to 3 plus 2i. So right here, this is the real part of z. So the real part of z is 3, and the imaginary part of z is not 2i, but is 2. Okay? Now, so we are going to look at the arithmetic of these complex numbers, and before we do that, obviously we need to know under what situation, under what circumstances two complex numbers are the same. So right here, the concept is very simple. So if you have two complex numbers, let's call it z1, which is a1 plus b1i, and z2, which is a2 plus b2i. Again, a1, b1, a2, b2, these are real numbers, and I squared is a number that is equals to -1. So we say that the two complex numbers are the same if and only if the real parts are the same, and also the imaginary part are the same. So for example, 2 plus 3i and 3 plus 2i's are not the same complex numbers because the real part here doesn't match. So for example, if I told you that a plus 4i is 3 plus bi, because of this equality, from the definitions, we will have to make sure that the real part is the same. That will give us a equal to 3, and then here the imaginary part here will have to be the same. That will give us b equals to 4. All right. Now, once we know the meaning of the equality of two complex numbers, we are going to look at how do we add and subtract two complex number? How do we multiply and divide complex numbers? Okay, so addition and subtraction is defined this way. So if you have two complex numbers, let's say one of them is a plus bi, another one is c plus di. How do we add them? So we add the real parts together. So a plus c, and then we add the imaginary part together, which is our b plus di. So this is how we define additions of two complex numbers, and this is how we define subtractions of two complex numbers. It's the same. So in order to do subtractions, you will take the real part of these two complex number and subtract them, and also the imaginary part. So for example, if you have 4 minus 3i plus 2 plus i, so you can write them as first add up the real part, so it will give you 6, and then add up the imaginary part. So because here this terms here is -3, so you add this terms here, the real number here is 1, so the imaginary part here is -2. So you have -2i. You can also subtract these two complex numbers. So the way we do it is we look at the real part. So the real part will be 4 minus 2, and then -3 minus 1. That will give you, oh, that's a typo here. Let's look at this again. So we have -3. So we have -3, and then we have -1. So this part here will be -4. So this is actually 2 minus 4i. All right, so this is how we add and subtract two complex numbers. Not very difficult. We can also multiply two complex number, and the way we do it is just treat the I as the numbers. And so these are all treated like numbers. These are all like numbers. And then we just multiply them by applying our usual distributive law and make sure that they are commutative, which means a times b and b times a is the same. So the way we multiply, we will be taking the a and distribute to get ac, and then a distribute to di, you will have a di. So a here is a number, d here is a number, I here is also a number. They are all numbers. Okay, so I is a number It's just a numbers in such a way that when you square this number, it will be -1. But I is a number, so you just have to treat them as a number. You just have to treat it like a number. So when you distribute, you will have AC, and then you distribute, you have ADI, and then again you distribute here, you will have BCI. They are commutative, so you can rearrange them to make sure that I is you can put it I as the last numbers. And then the last part here, if you distribute here, you will have BI times DI. So this will give you BD, and then I times I is I square, and I square is defined as -1. So you will have BDI square, which is minus BD. So once you have this, the convention is that we're going to group all the real part together. So all this real number here will be grouped together. That is how you get AC minus BD. And then the imaginary part here, so this imaginary numbers, I mean the imaginary part of a complex number. So all the things that is related to I will be grouped together, and you will factor out the I, and you will have AD plus BC. So this is how we write complex number in general. So we want to write a complex number as something, which is some real number, plus some other thing. It doesn't have to be the same. So let me use this triangle symbol. So you try to find a real numbers, and then another real numbers multiply I. So the reason why we regroup them is because all complex numbers should be in this form. So after you multiply them, technically speaking, these are already the correct answers, but still we want to put it in the form of some real numbers plus another real numbers times the number I. All right, so this is how we multiply two complex numbers. It is not difficult at all. You just distribute. So for example, here, so you have 2 plus 3i, one complex number. Again, look at the way we put them is always a real numbers plus another real numbers times I. So we have another complex number here, also written in the form of a plus ib. So now we multiply them, so we distribute. So this is going to give us 2, and then we distribute. This is going to give us minus 10i, and then this is going to give us plus 3i, and then this is going to give us minus 15i squared. And because I squared is equal to -1, so this part here is actually minus 15 times -1, which is positive 15. So that's how we get all these numbers. So the positive 15 together with the 2 will make a positive 17. This is the real part. And then the part that has I on it will be -10 and 3. So all of them, if you group them together, you will have -7i. So that is how we multiply two complex numbers together. Okay. So right now we are just basically trying to tell you how do we do arithmetic with the numbers. So because there is many deep consequences of all these complex numbers, but we are not going to talk about most of it actually. We're only going to talk about how we add, how we subtract, and we're going to talk about the polar form, how do we take exponential. There is entire calculus that can build on complex numbers. Those are known as complex analysis, and we're not going to talk about all that. Just in this section, actually in this course right now, this is basically just like a quick introduction of what complex numbers is about. So we're telling you what complex number is about, just like long time ago when you start to learn numbers. After you learn what numbers are, then your teacher will try to tell you how do we add them, how do we subtract, how do we multiply, and how do we divide. So we're going to do the same thing, just that now we have new numbers, which are called the complex numbers, and we are learning how to add, subtract, multiply, and divide. So the last operation is divisions, right? So if you have two complex numbers, 2 plus 3i, this is one complex number. And what is the meaning of this complex number divide another complex number? Now remember, we wanted to change this. So a complex number divided by a complex number will be still another complex number. So we want to figure what that complex number is. So that complex number is being complex means that it will be in the form of a box, which is a real numbers, and the form of a triangle, which is another real numbers, and then times I. So we have to figure out what is the box and what is a triangle. What is in the box? What is in the box? And what is a triangle? Right? So if you can do some kind of computations and change the whole thing to a box consists of a real numbers plus a triangle consists of real numbers times I, then you have finished the division operations. So let's look at it. So right now we have this. So 2 plus 3i over 1 minus 5i is the same as 2 plus 3i over 1 minus 5i times 1. So this is exactly the same complex number divided as the same complex numbers. The old rules is still hold here. This is still 1. All right. So what happens to the numerator? So the numerator we are going to distribute, and the denominator we are also going to distribute. Now for the denominator, just pay attention to the denominator, which is 1 minus 5i multiply 1 plus 5i. This is exactly in the form of what you learn in high school, which is a minus b and then a plus b. And we already know that this is going to give us a minus b squared, a squared minus b squared. Okay, so right here, this product here is going to give us 1 minus 25i squared. All right, so our a here is obviously 1 and our b here is 5i. So you're going to have 1 square. So right here, you're going to have 1 square minus our b is 5. So you're going to have 25. Sorry, our b is 5i. So you're going to have 25i squared. Now, I squared is negative 1. So I squared is negative 1. I squared is negative 1. So you basically have 1 plus 25 as the denominator. So the denominator is going to be 1 plus 25, which is 26. Now this is good news because we get rid of the I. There's no more I in the denominator. So the denominator is nothing but real numbers, which is 26. All right, let's look at the numerator. So the numerator, we just distribute as usual. So you will have 2 times 1, which is 2, 2 times 5i, which is 10i, and then 3i times 1, which is 3i, and then here 3i times 5i is going to give you 15i squared, and I squared is negative 1. So this is negative 15 plus 2, which is negative 13. And those that are related with I, we're going to group them together, which is going to give us 13i. So now, all the arithmetic that you learned before still hold true. So this thing can be written as this. As you can see now, we have a real numbers plus another real numbers times I. So this is, and by the way, 13 and 26. This gives us negative 1 over 2. And here they give us positive 1 over 2. So this division of two complex numbers give us another complex numbers. And this is what we are going to say the numbers that you got after you divide 2 plus 3i over 1 minus 5i. So this is how we do divisions for two complex numbers. So for division for two complex numbers, the key, as you can see, the key here is to make the denominator free of the I. And how do you make the denominator free of the I? You multiply something that looks like this. So if you have 1 minus 5i, you will want to multiply 1 plus 5i. So if you have a plus ib, you would want to multiply a minus ib. This is like one sure way to get rid of the I. In fact, as you can see, a plus bi. Oh yeah, by the way, so I'm used to writing I in front of the numbers, so but it's the same. So yeah, let's do it like this because your books do it like this. But if you see that I subconsciously put the I in front of the B, that's the same. That's not going to be a problem. So notice that a plus bi times a minus bi, you will get, as what we have discussed before, you're going to get a squared plus b squared. And because of its the way it operates in complex number divisions, and we use that all the time, we actually have a name for this. So for a complex number a plus bi, if a minus bi is known as the complex conjugate, the complex conjugate for this numbers. So a complex conjugate for that number, that's the notation z bar. So that is bar. So z bar is going to be a minus bi. So if z is this, z bar is going to be this. Now, so for example, if you have a complex numbers, let's say w is 2 plus 3i, the complex conjugate for 2 plus 3i is 2 minus 3i. So the real part never changed. The imaginary part will be deferred by a negative sign. So let's say you have z equals to 2 minus So let's say 3 minus 4i. Then z bar, the complex conjugate for that number, will be 3 plus 4i. Okay, and then if you have this, you will see that w times its conjugate is going to give you 4 plus 9, okay, which is going to be 13. So z times z bar is going to give you 9 plus 16, which is going to give you 25. All right. Now we can represent complex number as a point on a plane consists of the imaginary axis and the real axis, and this plane is called the Argand plane. The Argand, it's a French name. Call it whatever you want. So it's called the Argand diagram or Argand plane, and the Argand planes consist of the imaginary axis and the real axis. Now, technically speaking, you do not write this as I. You write this as 1, and it will be taking as 1. It will be taking as 1 times I. So let's say you have a complex number. So here these are all real numbers. Okay, so you have 1, 2, 3, -1, -2, -3, 1, 2, 3. -1, -2, -3. It's just like our coordinate system. It's just that we do not call the y-axis as y-axis. We do not call the x-axis as x-axis. We call the x-axis as the real axis and the y-axis as the imaginary axis. So every complex numbers can be represented as a dot, as a point on this diagram. So for example, 2 plus I, you will be 2, that's the real part, and then 1, which is here. So this point here is going to represent 2 plus I. And as you can see, this is going to represent 3 minus I, so on and so forth. Okay, so this is called the Argand diagram or the Argand plane. All right, so this is a picture for the conjugate. So if you have z, which is a plus ib, if you see that this is a plus ib and you need to put it in the Argand diagram, so this part here, the x coordinate, so to speak, is going to be a, and the y coordinate is going to be b. And the conjugate of this number is going to be a minus bi. So if this is a b, your minus b will be here, and this is the conjugate. So this is the Argand diagrams, representations of all these numbers. Now, one very important thing for complex numbers is to be able to convert it to something that we call the polar form. And in the second video, you will know why we wanted to put it in the polar form, because if we put it in the polar form, things will be easier. So let's look at how we are going to put a complex numbers, which is z equals to a plus bi, into a polar form. And now in polar, we say it's in polar form because it is really kind of like in polar form. So for example, this is the Argand diagram, and let's say that this is the a, which is here, and the b is here. So the complex number is represented as this point. Now, if you look at the distance between these 2 points, we can compute this distance pretty easily, and our Pythagoras theorems will tell us that this distance is the square root of a squared, because here is a and here is b. So this is a, this is b, so it'll be a squared plus b squared. Now we have a fancy name for this. So if you have a complex numbers, this thing here is kind of like the magnitude of that numbers, like how far away it is from 0. That particular magnitude is called the modulus of the complex numbers. So if you have a complex number z equals to a plus bi, the modulus of the complex numbers is defined as this distance. It's kind of like the r in your polar coordinates, right? So your r in the polar coordinates will be this distance, right? So this is your r, and that is the theta. So this r here is called the modulus, or the absolute value of that complex number. So every complex numbers, obviously, can be represented as a dot, as a point on the Argand diagram. And this thing here is going to be the modulus of the complex number. The notation is like this, which is kind of like the absolute value notations that we have for numbers. And that's also the reason why it's called the absolute, also known as the absolute value of z. Now, if you remember the way that we look at the polar form, once you have, it's a very simple high school trigonometric functions, application of high school trigonometric functions. So if this is z, that's the distance, and if this is the theta, this is your coordinates. This is Cartesian systems, x and y, and then by now it should be very easy for you to see that this distance here, this length here, is nothing but the distance, okay, modulus z cosine theta. So this part here is z cosine theta. This is the x part, right? And this is the y part, and the y part here is the modulus, which is absolute value of z sine theta, and that's your y. So if you want to write z equals to a plus ib, your a is this distance, the x distance, and it will be given by modulus of z cosine theta, if this is the theta, right? And then plus I, sorry, my problem again, right? So I will be here. So the number b will be this part right here, this part right here. The number b is going to be absolute value of z and then sine theta, and then that's the b, and then we times I. So now our z, instead of writing it as a plus bi, which is also known as the Cartesian systems, instead of writing it as a plus bi, you can also write it like this. And obviously, because they both have the absolute value of z, which is the modulus, you can factor that thing out and write as cosine theta plus sine theta I. Sorry, and this time right now you write I in front of it, because otherwise it will be confusing, right? So we write I in front of the theta. So that's the reason why it's easy for me to write IB. But anyway, so this part here, your z, instead of writing it as a plus bi, you can also write it like this. That thing here, that thing right here that you see is called the polar form. So this is the polar form of that complex numbers. And this angle theta here also have a very fancy name. So this distance here has a fancy name called modulus, and this theta here also have a fancy name. It's called the argument of z. So argument of z, the notation for it is this. So argument of z, when you see something like argz, it means this angle theta. Okay, so if you put it in the polar form, the r in the polar coordinate system, the r has a special name called modulus, and the angle theta has a special name called argument of z. All right, let's look at some example. So the way for you to write the complex number into polar form is to first write into use the Argand diagram and figure out what is the magnitude and what is the angle theta. It's actually pretty easy to do. So you find the magnitude, also known as the modulus, and you find the theta. Now, so let's say you are given 1 plus I, and the question is, asks you to write into a polar form. So you will want to write polar form. So z is 1 plus I. If you wanted to write in polar form, you have to figure out the modulus, and then you have to figure out the arguments, and you have to put it in this form, right? This is called a polar form. So we'll have to investigate what's the magnitude. Well, that is a preschool problem. So if you have a triangle, right angle, this is one, obviously the distance here is square root of 2. So that is the reason why we have this. So the modulus of 1 plus I is a real numbers, and it's known as this, which is in this case is square root of 2. So this is square root of 2. So next thing you need to do is find the theta, the arguments of that complex numbers. Now, so if you look at this angle, so this triangle, preschool triangle, this is one, you know that this is 45 degrees. And because we are all grown up now, we don't write 45 degrees, we write pi over 4. Okay, so this is going to be the arguments, pi over 4 plus I sine pi over 4. So this is called the polar form of these complex numbers. It's not difficult at all. And the convention is that we measure our angle. Okay, we'll talk about this in a bit. So we measure our angle from here. So if you're in the first quadrant, second quadrant, third quadrant, fourth quadrant. So if you're on the first and second quadrant, you measure angle like this. But if your angle is going to be on the third and on the fourth, you'll measure it from here. So as you recall, if you measure angle this way, it will be assign this particular positive sign, and if your angle, if it's measured this way, then you assign a negative to that angle. All right, we'll look at it in a bit. Just try to let you know right now. So the next example will be try to ask you to write these complex numbers in the polar form. So first thing you do is put it in the Argand diagram and figure out where exactly that number is. So every complex number will be represented in an eigendiagram. Actually, do you know that all the real numbers are also complex, because complex numbers is defined as all the numbers that can be written in this form. So all the real numbers can actually be written in this form by taking b equal to 0, right? So all the real numbers can be written in this form. So all real numbers are complex numbers, but not all complex numbers are real. So we will have a Venn diagram that looks like this. All the real numbers is complex number. By the way, the set of complex number is usually denoted by this, but not all complex number are real, but all real are complex. So this is it's not supposed to be a very surprising result. And by the way, you know where all our usual number line, you know where our usual number line is on the eigendiagram. It will be right here on the x-axis. Okay, so our x-axis is actually our typical real number line. Anyway, so back to this. There was a little bit of tangent. So we need to figure out where is this point. So this point, the real number is -2, the real part is -2, and the imaginary part is 2 square root of 3. So it's going to be here, and you know that this point here, this complex number here, will be represented by a point and it fall in the second quadrant. Now, how do we find the angle theta? Now, the modulus, I don't think that's going to give you any trouble. So the modulus is actually 4. But how do you find the angle theta? Now, don't overthink it too much. You just have to look at this diagram, and then you can look at the high school trigonometrics diagram, and look at this is alpha. This is 90 degrees. Forget about the -2. Just look at the magnitude. So this magnitude is 2, and this magnitude is 2 square root of 3. So if you take the tangent alpha, it will be 2 square root of 3 over 2. So it will be square root of 3. And you remember this triangle, you will know that your alpha, if your alpha is if your alpha is 60 degrees, right, which is pi over 3, then you will have tangent alpha equals to square root of 3. But we are looking at this triangle. But in fact, the theta, angle theta, the argument, is actually measured from here. So the whole thing is pi. Alpha is pi over 3. So the theta is nothing but pi minus pi over 3, which gives you 2 pi over 3. So all these things is actually pretty trivial. I mean, I don't want to give you any formulas how to compute all this thing, because once you put it into an eigendiagram, you will supposed to be able to figure this thing out, right? So our angle is measured from here. So our angle here is 2 pi over 3. Modulus is 4. So this complex number has this polar representations. It has these polar representations. This number here is 4, and the argument here, the number here is called the modulus, okay, is 4, and then the angle theta, which is called the argument of that complex number, is 2 pi over 3. All right, one last example. This time you are required to write this complex number in polar form. So which means that we will need to figure out the modulus, which is easy, and also the angle, the arguments. Now, so again, where is square root of 3 minus I on our eigendiagram? Well, square root of 3 is going to be here, negative I, which means that we're going to look at -1. So this point here is going to be our square root of 3 minus I. Okay, no big deal. So what is the magnitude, the modulus? Well, Pythagoras theorems tell us that it's going to be square root of 1 square. Why? Because this distance here is 1. This distance here is square root of 3. So we will have 1 square, square root of 1 square plus square root of 3 square. So it will be 4. Take the square root, it will be 2. So the modulus is 2. Okay, so the modulus is 2. What is the angle? Well, just draw the usual triangle. So this is square root of 3, this is 1. If you take tangent alpha, it will be 1 over square root of 3. And you will figure out from this diagram that your alpha is pi over 6. So your alpha is pi over 6, and you are in the fourth quadrant. So when you are in the fourth quadrant, you write your answers as this angle. So you are moving clockwise, so your angle will be represented by a negative sign, and then the magnitude of the angle, like how big is the angle? That angle is pi over 6. So once you have this, so you will report your angle as negative pi over 6, and then you will report that the modulus is 2. So this complex number here will have this polar representations, and that's the modulus, and that's the argument. So in this case, the argument is our theta is equals to negative pi over 6. So these are the basic. What we learn is what is complex numbers. Complex numbers are all the numbers that you can put it in the form of a plus ib, and then we learn how do we add them, how we subtract them, how do we multiply them, and how do we divide them. And during the division process, we introduce the concept of a conjugate, and then using the conjugate, you multiply a complex number with a conjugate, you will get a real number. So the I will be gone, and you will get nothing but just a real number, and we use that to do divisions, and then we introduce the concept of a polar form, and that's it. This is the first part of the lecture, and in the second part, we are going to look at something slightly more complicated, but this is, as I said, this is only an introduction, so nothing is going to be very complicated. We're just going to tell you what you need to know, or the basic on complex number, and I will see you in the second video.